I already watched the video, and so in your early math career you learned about 0 and 1. Later you learned pi, and for most students pi is the first example of an irrational number. And then we talked very, very briefly about the imaginary number, the square root of -1. So by now there are 4 or 5 important numbers in math, and he talked about how it makes the most beautiful formula in mathematics. This is the one that he showed. E to the I pi plus 1 is equal to 0. And it is true, if you type it into your calculator, the E button is above the division symbol, I is above the period, pi is above the caret symbol, and then if I add 1, I do get 0. And I should ask Dr. Loin to prove it for me, because I don't really understand why it works. When you think, you don't ever need it. It's just showing you that someone proved that there was this cool formula in mathematics. So what is E? E is the number that he was talking about when you compound interest continually, right? 1 was your original investment, and 1 over n is the interest. That's 1/12 of the time, or 1/365 of the time. And however many times you cut your interest into parts, you raise it to that power. So E is the number 1 plus 1 over n to the nth as n gets bigger and bigger to infinity, so you're doing continuous interest. And it's also the base of the logarithm, the natural logarithm that we're going to talk about next week. So I'd like you to find some of the early values of E by hand. So you can enter, they already gave you what 1 over n is. So in the third column in your chart, you're just going to add 1 plus 1 over n, fill in that column. And then I would do the fourth column of the chart like using your calculator. Do this number, the 1 plus 1 over n, and raise it to the nth power. So n is in this left column, right? So you're going to raise it to the first power, and then to the second power, and then to the fifth power, and then to the 10th power. So take a minute and calculate some of those values by hand, because it'll generate E as you get bigger and bigger values. End of the year, get your 100% interest, you're at $2. But if you do it every 6 months, you get less per every 6 months, but you end up with more in the end because your interest earned interest partway through the year. So, when you get up to 1,000, you're really close to 2.718. So was everyone able to find the button on their calculator? There is a button above the division symbol. That just gives you E. And there's also a button above the natural log symbol on the left column. So if you need to do E to a power, that'll give you E to the X. So there's 2 different E buttons that you probably never knew were on your calculator. And then this just restates E is the Euler constant. And then I'd like you to use your calculator to find E squared and E to the negative first, and then we're going to use those values to graph our E to the X graphs. So calculate E squared and E to the negative first. E squared should be 7.4. Nearest hundredth, 7.39. And then E to the negative first, did you get 0.37? All right, so if we wanted to graph E to the X, we know that at 0, E to the 0 power, it will always be 1 because it'll have the same y-intercept as all of our other graphs, right? 2 to the X, E to the X, and 3 to the X are all very similar, right? Because E is just 2.7 to the X. So steepness-wise, it's going to be very similar to 2 to the X or 3 to the X. So when I go over 1, I would go up E, 2.7. And when I go over 2, I'm going to go up 7.39. And when I go over to -1, I'm at 0.37 because I just generated those 2 values. So E to the X is a curve that just looks like 2 to the X or 3 to the X, just a different steepness. It still has that asymptote at y equals 0. And what would be the difference between A and B? What's the only difference in these two graphs? What does a negative x do as a transformation? Flips it which way? Please tell me you know this. Negative x, all the x's that are on the right get flip-flopped and are now on the left. So it flips it over that y-axis. So e to the negative x would just be 1 over e. So it's just a decay graph of the same values. So at -2, you're at that 7.39. At -1, you're at e, and then 1, and then 0.37. So it's a decay graph, right? And then y equals 0. And then what would that x plus 2 do to the graph? So just using the transformation rules on a new base. What does plus 2 do to the graph? Goes to the left. Good. When it's x plus 2, it is left 2. So I can take those original data points from part A and just shift everything left 2. So left 2, E, and then we'd be at 7.39. So my y-intercept would now be 7.39. And my asymptote is still at y equals 0 because I only shifted left or right. And then at the bottom there it just says, what 2 interesting facts about the graph of e to the x were stated in the video that make the graph and the constant e very important in calculus? Why is e to the x important in calculus? Can anyone tell me what they heard? Area under the curve. So calculus is the study of derivatives and integrals. Derivative is the slope of the line at that point. Integral is area under the curve. So if e to the x at any point on the curve, right, so on the graph of y equals e to the x, any point on the curve has the same y value. He called it the gradient, but I think that's the British term for derivative. So I'm going to call it the derivative. That's what we call it in calculus. And area under the curve, which we call the integral, but I think you saw how they shaded it. So any point on this line, well, I'll go to the parent graph, e to the x. So if I was at this point, right, we just found the y value was 7.39. The instantaneous rate of change at that point is also 7.39. And if I shade it in under the curve all the way down here to -infinity, this kind of triangular region has an area also of 7.39. So because you're working with derivatives, integrals, it's the natural language of calculus. All right, so